Yes, Professor Hou. It's your time.
All right. First, I would like to thank you for the invitation to your seminar. And my talk is about the number of equivalence classes of Boolean functions. Okay, my talk is divided into 4 sections: an introduction, and the number of equivalence classes of Boolean functions, and then we will talk a little bit about the compound matrices, and finally, the solution to a question by Magrimus and Sloan. Introduction. We know that, by the way, do you see that the top of my slide is blocked by this bar? Can anybody tell me how to get rid of this function bar, the toolbar?
You can move it to the right-hand side, for example. You can move it, but
how do that work?
You just use your mouse and click on it, and you can slide it into.
Just drag it to the.
Yeah.
Right.
Yeah. It's not a big problem from our viewpoint. We can only see your slides.
But I have a title. Every time I have a title. And
your title is functions from F2 to the N to F2, right?
You can see the title, right?
Yeah, I can see the title, no problem.
Oh, I can see the title. I cannot. That's the problem. Okay.
Oh.
Yeah, I understand what my view is blocked, but your view is not. Okay, that's good.
Yeah.
Okay.
Mm-hmm.
So we know that. Well, let's first define what's so-called reduced polynomial. So a polynomial in n variables over F2 is called reduced if the degree in each variable is at most 1. We know that every function from F2 to the n to F2 is uniquely represented by a reduced polynomial. And this way we can define the degree of a function, because it is represented by a reduced polynomial, and we will just use the degree of the reduced polynomial to define the degree of the function. So here is an example. So suppose I have a function, so from F2 to the 5 to F2. Okay, so this is the definition of the function. And this function is represented by the reduced polynomial x1, x2, x5, x2, x4, x5 plus x3. The capital Xi is indeterminate, and the little xi is just an element of the field F2. And you see that whenever you see, say, x2 to the power 3, you can replace it with x2, because in the field F2, x squared is equal to x. Okay. All right. Then we look at the set of all functions from F2 to the, I'm sorry, here should be F2. This should be F2. Okay. I gave another talk in which the field is FQ. So here everything is over F2. Okay. All right. And then we look at the functions from F2 to the n to F2 whose degree is less than or equal to R. We collect all such functions, and it's of course a subspace of the space of all functions from F2 to the n to F2. And this subspace is called the rth order read-molar code, and the length is 2 to the power n. And why it's called a code? Because each function from F2 to the n to F2 can be treated as a code word of length 2 to the power n. Here, you simply enumerate all the elements of f2 to the n, and you exhibit all the values. And this is also called the truth table of the function. Okay. And we have an ascending chain, an ascending sequence. Now, the read molar code of order -1 is defined to be 0, the 0 subspace. And then you have the 0th order read molar code, which is the collection of constant functions. And then here you have collections of functions of degree 1, polynomials of degree 1, or you might want to say f-on functions. And when you reach R, the nth order, you have the ambient space of all functions from f2 to the n to f2. Right, so we have this nice ascending chain. The f-on linear group, well, when you think about the f-on linear group, you think about f-on transformations. But algebraically, it is more convenient to treat f-on linear group as a subgroup of the general linear group of degree n+1. So here you have an invertible matrix. You can see my cursor, right, on the slides, right? So when I indicate something, you can see it, right?
Yes, I can see
it.
a
little hand?
Yes, no problem.
Okay, so that's good. That means that I'm not just talking to myself. Okay.
Yeah.
Okay. So this A is an invertible matrix, and this little a is a vector, and you form a matrix of a square matrix of size n+1 by n+1. And well, so for each element in the f-on linear group, you have an action of the element on the functions from f2 to the n, from f2 to the n to f2. The action is quite simple. You simply apply the f-on transformation to the variables. So you start with a function f, which is a, you might want to say a polynomial, reduced polynomial in n variables. And then you apply the f-on transformation. So this is the linear transformation plus the translation. So you apply the f-on transformation to the variables. The result is called sigma of f. In this way, the f-on linear group acts on the set of functions from f2 to the n to f2. Okay. And it is quite obvious that this action preserves the degree because f-on transformation will not increase or decrease the degree. We're talking about the invertible f-on transformations, right? So the f-on linear group maps any read molar code of all, maps a read molar code of order R to itself. And in fact, in most cases, the f-on linear group is actually the entire automorphism group. This is true when R is between 1 and n-2. In the remaining extreme cases, when R is -1 or 0 or n-1 or n, in that case, the automorphism group of the read molar code of order R is the entire symmetric group of the vector space f2 to the n. Okay. All right. Here is a nice duality theorem. It says that, well, first, we know that the f-on linear group maps read molar code of any order to the same to the read molar code of the same order. Therefore, the f-on linear group acts on quotients of read molar codes. So if you look at this quotient, that's rth order mod s minus first order. Here, when you think about this quotient space, it's actually the linear space spanned by monomials of degree between S and R. So here in this picture, I've shown you this interval from S to R. If you collect any monomial of degree in this interval, it's in this quotient space. And actually all such monomials form a basis of this quotient. All right. And then, okay, the theorem says that the orbits of this quotient under the action of the affine linear group is the same of the AGL orbits of another quotient. This time is the quotient of S prime of order S prime over the order of R prime minus 1. So S and S prime are related by this relation. S plus S prime is equal to A. And R prime are related by the same relation. So if you look at this picture, you have this two intervals, okay, symmetric with respect to the midpoint between 0 and A. So the number of affine orbits in this quotient is the same as the number of affine orbits in the dual quotient. Okay, but the proof of this theorem is not too difficult. It's a basic some linear algebra method. Okay, it's not difficult. All right, so let's move to the next section. Number of equivalence classes of Boolean functions. Numerical results and a question by McGreamus and Sloan. All right. So first let's define the affine equivalence. Now two functions from F2 to the N to F2 are called affine equivalent if there exists an element in the affine group and a element in the first order written molar code. That is to say, H is a polynomial of degree at most 1. Okay, such that this function G is obtained by first performing the affine transformation to the variables inside F, and then added by a linear polynomial. So this is the meaning of equivalent, affine equivalence. Okay. Why people are interested in this kind of equivalence? Well, main reason is this: if F and G are equivalent, then they are cosets. Okay, the coset of F and the coset of G of the first, the coset of first order read molar code containing F and the coset of the first order read molar code containing G have the same weight distribution. And this is easy to see because if you apply an affine transformation, you're going to keep you're going to just shuffle the elements in the first order read molar code. And if you add another element in the first order read molar code, you're going to just again shuffle the elements in the first order read molar code. And this is the reason that the cosets of F and G have the same weight distribution. Why people are interested in the weight distribution of a Boolean function of the first order read molar code by a Boolean function? Well, in cryptography, the minimum weight of the coset F plus the first order read molar code is called the nonlinearity. It's called the nonlinearity of F. And Boolean functions with large nonlinearity are well solved out in cryptography. Supposedly, they're good for a number of reasons.
Here's a question.
Yes, please.
Yeah, so for Boolean functions, is it true that Fi equivalence is the same thing as CCZ equivalence?
No, no, it's not.
No.
That's slightly different.
I see.
That's slightly different.
Okay, I see.
Maybe I can turn up the volume a little bit. Okay.
Okay.
Okay. Okay. This thing is really strange. I lost my. Okay. Yeah. For a moment, I couldn't find my cursor. Okay.
I see.
All right. So now we're talking about the number of equivalence classes of functions from F2 to the n to F2. The number of equivalence classes. Okay. So I will simply use a capital N sub n to denote this number. And we know that from the previous slides, you can actually see that. Saying that F is equivalent to G is equivalent to saying that these two cosets are equivalent under Fn transformation, right? So the number of equivalence classes of functions from F2 to the n to F2 is the same as the AGL orbits of this quotient space. And then, as we call the duality theorem, this number is the same as the number of AGL orbits in the dual quotient space, which is, let's see, over -1. I think it's over -1 over the first order.
Yeah, that's -1, the 0.
That's which is 0.
Yeah,
which is
yeah.
0. Okay. No explicit formula for this number is known. So that gives people incentive to, play with this number. Okay. No, so there's a big open question here. So here are some numerical results. First, let me mention that this capital NN is listed in the online encyclopedia of integer sequences as A001289. So, so people computed this number over many years. Okay, when n is from 1 to 4, quite obvious. Okay, you don't need anything. You can easily determine those numbers: 1, 2, 3, 8. And then in 1972, Burley-Camp and Welch determined that the number of N5 is equal to 48. Actually, they classified all the cosets of the read-molar code R1, of the cosets of the read-molar code R15. And they determined that there are 48 equivalence classes of such cosets. Okay. Then many years later, 1991, Marona computed N6. It's this number, okay. And then let's see. I think it was many years ago. Okay, when I was still very much interested in the read-molar code, I computed N7. It's much larger. Okay, okay. At that time, I did not have any fancy thing. I did not have a Mathematica. The way I computed, actually, I computed the number modular several primes, and then we used the Chinese remainder theorem to recover the precise integer. That was a long time ago. Okay, now you don't have to use Mathematica or other things. They will give you precise integers. Okay, now the story goes on. Very recently, Zheng and Yang in 2019, they computed additional values of this sequence. N8 is this number, and the table is a little bit too small, so move to the next slide. They also computed, in the same paper, they also computed N9 and N10. Okay. I guess if they want, they can continue on. So these are the known numerical values. And here is a question by McGreemus Sloan, and this question this is a well-known question. Okay, it appeared in their book. Their book is what the introduction. What is that book? Theory of error correcting codes. This question appeared in their book as research problem 14.2, and the question asks for an asymptotic formula for this sequence as n goes to infinity. All right, so recently we found a solution to this question, and you will see the answer in just a moment. Okay. So here is the third section of my talk, compound matrices. As a matter of fact, our solution to the question by McGreemus and Sloan relies on compound matrices. However, compound matrix has its origin from a different problem. It's not from read Molar code or Boolean functions. Its origin is the exterior product of a vector spaces. Let's first define the compound matrix. Let little r be an integer between 0 and n. And let let's just call it n choose r. This is C script C n r. Let's just call it n choose r. So let n choose r denote the set of all r element subsets of the set 1 through n. So the collection of subsets of size r from 1 through n. So let's start with the n by n matrix over any field, no restriction on the field. Okay, and we define the off compound matrix of A in the following manner. So this off compound matrix is denoted by C sub Ra. It is a matrix of size n choose r by n choose r. Its rows and columns are indexed by the elements of n choose r. So the rows and columns of the compound matrix are indexed by r element subsets of the set 1 through n. And then how do we define entry? Let's say ST entry. So S and T are two subsets of 1 through n of size r. Then we can just carve out a sub-matrix, okay, whose, let's call it AST, whose row indices are from the subset S. and the column indices are from the subset T, and we use the determinant of the submatrix as the ST entry of the compound matrix. So if I show you an example, you will see there's nothing mysterious here. Okay, so here's an example. So let's take F2 as the field, and let's start with a 4x4 matrix. 4x4 matrix. Right? And we label the rows and columns of the second compound matrix. I'm talking about C2A. So I enumerate all the 2-element subsets of 1 through 4. So there are 6 of them. Okay, 4 choose 2, 6 of them. And then what do we do? Okay, then we just say, for example, let's take 1, 2 and 1, 3. So 1, 2 as the index set for the rows of the compound compound. So 1, 2, I take 1, 2. So first row, second row, and 1, 3. So first row and third column, first column and third column. And when I look at the intersection, I get a 2x2 matrix, which is this one. Okay. So you get the idea. So this is how you get the compound matrix. The second compound of this 4x4 is a 6x6. Okay. All right. As I said, the compound matrix has its origin in the exterior product of a vector space. So let V be an n-dimensional vector space over any field with the basis E1 through En. So let this wedge RV denote the rth exterior power of V. Okay. Exterior product, just like the ones they use in differential geometry. Okay. Let's consider a linear transformation from V to V. So this is a linear transformation of the original vector space called F. Let's assume that the matrix of this linear transformation with respect to the chosen basis, E1 through En, let's assume that the matrix of F with respect to this basis is A. This is an n by n matrix. Now, this linear transformation automatically induces a linear map, a linear transformation from the exterior product to itself. And this exterior product is denoted by a wedge RF. Okay, you simply apply the linear transformation to the components in the wedge product. And then this is a linear transformation, and it should have a matrix with respect to the standard basis of the exterior power. The exterior power has a basis, EI1 wedge, EIR, where I1 through IR are strictly increasing. And therefore the basis of the exterior product is actually indexed by element subsets of 1 through n. Okay. And it turns out that the induced map of the linear transformation on the exterior product with respect to this basis is precisely the rth compound. Now, since the exterior product is a function, and we automatically have this equation, the rth compound of AB is equal to the product of rth compound A times is equal to the product of rth compound of A and rth compound of B. So this is automatic from the functoriality of exterior product. Here's another very useful property. If you know the eigenvalues of the matrix A, let's say the eigenvalues are lambda1 through lambda n, which are counted with multiplicity, then you can easily tell the eigenvalues of the rth compound. They are you simply form all the possible product. You simply form the product of all possible R eigenvalues, okay, including multiplicity, okay, and then you will get all the eigenvalues of the compound matrix, okay, including multiplicity. All right. So there is a. I don't want to go this way yet. Okay, so there is an easy way to tell the eigenvalues of the compound matrix from the eigenvalues of the original matrix. There is another useful property. This next property turns out to be very useful in the proof of in our solution to the question by McWilliams and Sloan. When you read it, as soon as you spell it out, you'll find that it's totally reasonable. Okay, so let's say A is an m by m matrix, square matrix. B is an n by n square matrix, and you choose an integer k between 0 and m, and you choose an integer l between 0 and n. And then you have the kth compound of A and lth compound of B, and you can form the tensor product. It turns out that this tensor product is a principal submatrix of this compound. Okay, what is this compound? Okay, first it is a compound of the block sum of A and B. Block sum, this is the definition of the block sum. And the order is K plus R. So we're saying that this tensor product is the principal submatrix of this larger compound matrix. Okay. There are other useful properties that we are used in the solution to the question, but I'm not going to detail those. Okay, there are other useful properties which I'm not going to detail. Okay, so the last section of this talk, solution to the question of the question by McWilliams and Sloan. So here's our answer to the question. It's just this simple formula. What it says that is that as n goes to infinity, the number capital N sub n is just like the reciprocal of this fraction. This top is a constant. It is a convergent to infinite product, so it's not important. It's a constant. It's a non-zero constant. And what's important is the denominator. So basically, capital N sub n compels to this quantity. So that answers the question by McWilliams and Sloan. And now let me outline the proof of this. Outline the proof of this theorem. Okay. I should stop at the end of 45 minutes, right?
Yeah, I think you have maybe 15 minutes to go.
Okay, that's more than enough. That's more than enough. I will stop. Okay. So first, we know that this number, capital N sub n, is the number for AGL orbits in this read molar code. So you have the situation of a group, finite group, acting on a finite subset, and you want to know the number of orbits. Therefore, you can use Burnside's lemma. Okay, Burnside's lemma says that where this number of orbits is equal to 1 over the size of the group times this sum. Well, this little sigma runs through the entire group, and this fixed sigma is somehow I changed the sigma to alpha, but okay, this should be sigma, okay? This should be sigma. So this fixed sigma is the number of fixed points of sigma in the set. Okay. So you can separate the term when sigma is equal to identity from the rest of the sum. So when sigma is identity, so the number of fixed point is the cardinality of the read molecule of order n-2. And then I have a summation where sigma is not equal to identity. Okay. Now, when you look at the quotient of the two red expressions, okay, this is precisely the reciprocal. Well, this thing appears in the theorem. Actually, the reciprocal of this thing appears in the theorem. Let's see if we still have that, right? And whether this is a finite product or infinite product, it doesn't matter because it's a convergent infinite product. So it really doesn't matter. So it boils down to the following. We only have to prove that the summation in the blue color is of a smaller magnitude compared with this term. Well, the size of the second order of a read molecule of order n-2 is well known. Okay, it's very easy. So this is the size of the read molecule of order n-2. So it all boils down to proving that the this summation is little o of 2 to the power n-1. Okay, it is very important that we exclude the identity away, and so the term where sigma is equal to identity is the dominant term, and the other terms all combined are not as big as the dominant term. That's the main idea. All right. So in order to estimate the estimate of what the summation in blue color, we do the following. We first introduce this notation for any subset, capital S, subset of 1 through n. We use capital S as to denote the product of xi, where I is from S. And in this way, we look at capital capital X sub S, where S runs through all subsets of 1 through n of size at most n-2. In this way, we get a basis of the read molecule of order n-2. So this is the basis. If you take any non-identity element, okay, non-identity element in the affine linear group, well, it acts on this read molecule as a linear transformation. Although it is the affine, it is from affine linear group, but when it acts on this read molecule, it acts on it as a linear transformation. And therefore, it has a matrix with respect to, say, this basis that we have just defined. And you can write you can write out the matrix of sigma with respect to this basis to some extent, not entirely, but you can say that the matrix of this sigma with respect to this basis is a block, is a lower triangular block matrix, where the diagonal blocks are compound matrices of order n-2, n-3, all the way to 0. You have no control of the things that appear at the lower triangle, but the upper triangular entries are all 0. And we know that the number for fixed point is simply 2 to the power of a nullity of this matrix minus identity. Okay, so this nullity is actually, what is it? It is actually the dimension of the eigenspace that belongs to the eigenvalue 1 of this matrix. But this nullity is not explicitly known, because nullity here is the, here remember that nullity is the geometric dimension. It's not the algebraic dimension. It's, I mean, the geometric multiplicity of the eigenvalue 1, not the algebraic multiplicity. Algebraic multiplicity is quite easy, but geometric multiplicity, in this case, we don't know precisely. All we can do is to estimate. Okay. Now, using various properties of the compound matrices, we can estimate fixed sigma in several cases. Okay, in the first case, we assume that now remember that the element sigma has a matrix part and a vector part. The sigma has a matrix part and a vector part. Okay, capital A is the matrix part and A is the vector part. Okay. So in the first case, we assume that the eigenvalues of the matrix A, there is at least one eigenvalue of A which is not equal to 1. In that case, we can show that fixed sigma is bounded by 2 to the power n minus 1. In the second case, we assume that 1 is the only eigenvalue of A. If 1 is the only eigenvalue, then all the elementary divisors of A are x minus 1 to the power of something. Is the power of x to the power, is the power of x minus 1. So in the second case, we assume that A has an elementary divisor x1 minus x minus 1 to the power m, where m is greater than half of n. In this case, we can show that fixed is bounded by 2 to the power n minus, this is about n over 2 choose 3. And then in the third case, once again, we assume that 1 is the only eigenvalue of A. But this time, we assume that A has an elementary divisor, x minus 1 to the power m, but here m is at least 2, but less than half of n. In this case, we can prove about this, we can obtain about the same upper bound, 2 to the power n minus n over 2 choose 3. Okay. In the fourth case, we assume that the matrix is simply identity. Since the affine transformation is not identity, then the vector part must be non-zero. So in other words, in this fourth case, the affine transformation is a non-zero translation. This is the easy case. In this case, we can show that fixed sigma is the cardinality of this read model code. Order n minus 2, length is 2 to the power n minus 1. And this is the quantity, it's 2 to the power n minus 1 minus 1. Okay, so we have 4 cases. In all 4 cases, we always have fixed sigma less than 2 to the power n minus something like n over 2 to 3 when n is sufficiently large. Therefore, if you look at this mention, sigma is not identity. So how many terms? Actually, the order of the group minus 1, but I don't really worry about that 1. I just say order of the group. And then each term is at most this. The order of the group is 2 to the power n squared plus n. And then you have this part. Okay. Well, let's see. If you look at this binomial coefficient, is a cubic polynomial in n, correct? Cubic polynomial in n. Here you have a square of n and a linear n. So you have a negative cubic term that will be dominant.
Yeah.
So I will be able to say that this entire expression is little o of 2 to the power n. And since I have a negative cubic term, I can just say, actually I can put any quadratic term, polynomial in here, but I just choose to use minus n minus 1 because let's recall that this is the goal. Yeah, because this is the goal that we set up a moment ago. We want the summation where sigma is not equal to identity to be little o of this exponential function, 2 to the power n minus 1, and we have achieved just that. So that the proof of the theorem is complete. So let me give you some references and just take a quick look. References. And this result will appear, this is the result that will appear soon in IEEE Transactions and Information Theory. And the archive version of this paper contains some typos, so please tolerate that. And with that, I just want to say thank you for attending my talk. And so that's it.
Yeah, thank you so much, Professor Hou. Let's clap for the very nice talk. Okay, now is the Q&A session. There is actually one question in the chat. Can you see the chat? Yeah.
Chat? Okay,
yeah.
Let me open the chat.
Uh-huh.
For case 3, is that supposed to be floor and choose 3, or are we using general binomial? When we use the binomial coefficient, the top does not have to be any. It does not have to be an integer. It could be anything. It could be a complex number. It could be from anything. It does not have to be, because if you look at the definition of the binomial, you only need the factorial. You only need the bottom to be a integer. The top does not have to be an integer. Does that answer the question? You can talk about x choose 3, where x could be a variable. Does that make sense? I'll just write it.
Yeah, there's a follow-up question in the chat.
So it wasn't typo. I mean, I could warn you, but it's a really. I'm used to this kind of thing. So not a typo.
Okay.
Not a typo. Not a, yeah, it's not a typo.
Yeah, it is not.
Not a typo. Let's just say A choose B is defined. My laptop is not defined.
Yeah, I think the student gets the idea. Yeah. Actually, I have a question related to the compound matrix method. So can it be used to determine the number of, for example, band functions?
Before you can you tell me how to reply it? Can I just I typed it. How do I reply it? Do I say send it?
Yeah,
everyone?
Maybe you just press the enter.
Press the enter. Okay.
Yeah, yeah, I can see that. Yeah. Okay, so that question has been answered. Here's my question. So is it possible to apply the compound matrix idea to count the number of, for example, band functions? Yeah, get a asymptotic formula, something like that.
Asymptotic formula, right?
Mm-hmm.
Well, here there is a big difference here. The total number of Boolean functions is trivial, is known. The total number of Boolean function, band functions, we have no idea, not slightest idea. So there is a difference. If you're talking about the equivalence classes, that's at the next level. And I don't know whether you can just go direct into equivalence classes without even knowing the total number of
okay.
number of band functions. So basically, we're talking about a group acting on a set, right. And we talk about number of orbits. If you don't even know the cardinality of the set, I think it would be say about right.
Yeah. I gotcha. So that is sort of premature question. We should first figure.
Maybe that, I mean, this is my just the answer that right on top of my head. It might be some other ways. I mean, you got useful information. Maybe not just precise. Actually, there are some questions. People can talk about, say, quadratic band functions. Then people talk about equivalence. You're aware that people are already doing that, right? For quadratic, they can talk about a number of equivalents. So still, there are relevant questions people can.
I see. Yeah, thank you. So, any more questions?
Well, thank you for a very interesting talk. I was wondering if you can get some other statistics from your method. Like, for example, if we averaged over all equivalence classes, if you can get the average nonlinearity or something like that.
I'm sorry, can you speak a little bit louder? For some reason, I can't.
I was wondering if you can get some other statistics from your method. Like
statistics, right?
Sorry?
Do you mean?
I mean statistics on the Boolean functions. Like, for example, the average
I see. Statistics, other statistics and Boolean functions, right?
Yeah.
Well, let me maybe, I don't know whether this answers your question or not. Maybe at least it's relevant. Let me just bring my slides to here, okay? So here you see that the affine linear group acts on the quotient space of read-model code. People can talk about, people can look at different quotients, and people can still talk about orbits. And for example, if you look at, say, rth order mod R minus first order, then you will be talking about homogeneous Boolean functions, correct?
Mm-hmm.
So, so if you can determine the number of orbits, then you will be able to say, you will be able to tell the number of equivalence classes for homogeneous Boolean functions of a certain degree. And I think that there are certain people who are interested in homogeneous Boolean functions. So subclasses of Boolean functions, you can talk about statistics or like that. I don't know whether it answers your question or not. Maybe direct and not direct answer to your question, but that's probably all I'm aware of.
Thank you.
Okay.
Yeah, thank you for the question.
Okay.
Yeah, so if no more questions, let's thank Professor Hou again. Yeah, and let me stop recording.